and then, oops, it doesn't have an answer. Right? Does that make sense? All right, so that's just warming up. You know, in some ways, we already did a lot of those, right? The difference between there exists an algorithm for every input versus for every input there exists an algorithm, right? That was a bigger case. So here's another model of computation where we're allowed to flip coins, right? So here's a simple problem. We have indoors that are closed, and between and what we're doing is it's a promise problem, all right? So I'm going to promise that behind half of the doors there's a prize. Now there's goats involved, so you can decide either you like goats and goats the prize, or you don't like goats and goats the not prize. But either way, right? And so what is an algorithm to this problem? The goal is the input is which doors have prizes and which don't, and the algorithm then decides which doors to open. All right? And the input, as I said, has the doors. And now, how do we normally do computation, right? There exists an algorithm for all inputs, right? So the algorithm guy has to say what the algorithm is, and then the adversary comes up with the input, all right? It gives you the worst case input. So I wrote it on the board, but here it is. There exists an algorithm such that for all inputs, the algorithm finds a prize, and the running time of the algorithm on the input is at most t. T tells me how many doors do I have to open. All right? So I want everybody to think about this. The worst case running time, right? I give you an algorithm which tells you which doors to open, and then the adversary chooses where to put the prizes. How many doors does the algorithm have to open to ensure that the algorithm finds a prize? Remember, half the doors have prizes. Anybody want to say something? N over 2 plus 1, right? Did everybody get that? N over 2 plus 1, right? Why? I have an algorithm that claims to work, right? So now this guy knows which N over 2 plus 1 doors you're going to open first. And one might argue, well, when the algorithm opens the first door, what it does, which door it looks at next, depends on what it sees in the first door, right? I mean, it's an adaptive algorithm, right? So what does the algorithm do? It says, I'm going to open door 5. And after it opened door 5, based on what it sees, it decides what to do next, right? But the adversary is going to kind of run the algorithm saying, oh, you opened the door and you didn't find a prize, right? So then it's deterministic what the algorithm does next. It goes and opens door 8. Oh, there's not a prize. And it opens door 27. Oh, there's not a prize, right? So he knows the first N over 2 doors he's going to look at. And what does the algorithm do? He comes up with the input where those doors don't have prizes, right? And so, in fact, that's what the algorithm's going to do on that input, right? Does that make sense? And then the plus 1, right? The algorithm looks at that one next door, and it's promised to be a prize. Everybody get that? Don't be too enthusiastic. We got one head nodder. The rest of you are dead. Thank you. All right, so have you learned quicksort? I made this slide for 3101, but so maybe you don't know quicksort. Anyway, quicksort is an algorithm in which you flip coins. You might have heard that there are randomized algorithms. right? Right? So you might say it feels unfair that the time complexity of this problem is n over 2, right? And anyway, what is quicksort is you choose a random pivot and you pivot based on it and you split based on the pivot. And we don't need to, we're not covering that. All right? But what's true about quicksort is on the worst case input, the sorting time is n squared. But if you're allowed to flip coins, then the expected running time is n log n and fast, a fast n log n. All right? So we want to be able to flip coins, and you might wonder how flipping coins help. And it all has to do with this game that I'm proposing to you, right? So, so here we have the game as we had before, right? So the algorithm is going to tell you, is going to announce what the game is. Sorry, what the algorithm is, right? It gives you the Java code, right? And the adversary who chooses the input knows the Java code, right? But what's the difference here? What does the adversary not know? It doesn't know the coin flip, the results of the coin flips, all right? The Java program says it's going to flip coins, and it says that if it comes up heads, it's going to do this, and if it comes up tails, it's going to do this. But the adversary doesn't know the result of the coin flips, right? So that's what he does. He gives an algorithm. It's going to open up. In fact, I'll tell you what the best algorithm is. Randomly choose a door and open it, right? Then randomly choose a door that you haven't seen before and open it, right? It's a good algorithm. All right, so and the problem with this is the algorithm now is symmetric over the doors, right? The adversary has to choose the input, i.e. where to put the prizes, but there's no difference between the doors, right? So the adversary knows the algorithm, but not the coin flip. He has to come up with the worst case input, but doesn't know what input to come up with. He doesn't know where to put the prizes, right? And if the doors are open randomly, it doesn't matter where he puts the prizes, right? Does that make sense? So he puts the prizes somewhere, and then we could flip the coins, right? And how the coins come up, heads or tails, doesn't depend on the algorithm. It doesn't depend on the input. They're random coin flips, right? And then, and then the coin flips, of course, determine which doors are opened. And now they're no longer sort of worst case inputs about where to put the prizes, right? They're worst case coin flips, right? Given we know where the prizes are, they're bad coin flips, but they're not bad inputs, right? And then what we want to test is our algorithm with the given coin flips and given where the prizes were put, does it find a prize or not? Right? Everybody see this? Now here we have an exists, and here we have a for all, right? So what are we going to put in here for the coin flips? Right? Half the doors have prizes, each door, right? So if you choose a random door, right, what's the probability you find a prize? 1 in 2, right? You find a prize with probability of half, right? And And so then we could talk about time, right? Here, this is the statement that the time happens in a fixed amount of time. All right, so now it turns out you're all going to be excited to know that there are two definitions of random algorithms. One's called Las Vegas and one's called Monte Carlo. And I can tell you what the two definitions are, but I would never be able to tell you which is which. But it's like left and right. Once I know this is my left hand, then I know this is my right hand. All right, so what are the two, right? So if you keep flipping coins, right, what's the probability that after I open T doors, I don't find a prize, right? It's, well, I fail and I fail and I fail and I fail, right? A half to the T is the probability I don't find a prize, right? So, right, so for example, if I open up 10 doors, then it's 1 in 1,000. If I open up 20 doors, it's 1 in 1,000,000. 30 doors, it's 1 in 1,000,000,000, right? The probability that I find the prize is 1 minus that, right? So one thing we could say, in fact, there actually, I can think of 3 definitions now of running time. Here we're talking about probability, right? The probability that I fail to get the right answer, right? Sorry, here the probability of getting the right answer is all but exponentially small, right? And oops. Oh, I guess I don't write it here, but here we're going to say we always have the right time, right? So the one definition is that the running time of your algorithm is bounded by some fixed amount, right? And we want to know what's the probability of getting the wrong answer or the right answer, right? All right. Here's another algorithm. This is the second one, where you just keep opening doors until, yeah?
The assumption that the algorithm could choose a door it's already previously opened, right?
Yes. Right. So he's very right here. The algorithm I told you was that you randomly choose a door you haven't seen before. And that is better than choosing a random door, right? But he's absolutely right. The math I did here was you just keep choosing a random door, and you might choose the same door more than once, right? And the reason I did that math is because it's a lot easier, right? If we calculated the other algorithm, it would be mildly better, right? But not better enough that it's worth doing the math for, right? We can leave it as a homework exercise, right? It doesn't really, for example, if I'm only opening half the doors, it doesn't get better until I've opened up more than half the doors, right? It doesn't get much better.
Also guarantee that you find
It's better. Yeah, 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 exactly. All right, so yeah, the probability becomes 1 after, yeah, exactly. So it's better, and I didn't do the math. All right, so now what we're going to do is we're going to keep opening doors, and we're going to stop when we find a prize, all right? So here's a fun problem. Think about what's the expected number of doors that I need to open. Anybody have an idea? Let me ask a problem that might be easier. And the reason it's easier is actually because it's harder. I'm going to roll a dice, a 6-sided dice, and I'm going to keep rolling this same dice until I get a 1. What's the expected number of times until I get a 1? What's your intuition? 6, right? If that's your intuition, you're right. So now I'm flipping a coin. The probability is a half that I get a prize. What's the expected number of doors I have to open till I get a prize? 2. 2, right? Right? So now what we've changed is we put a for all here, right? For all coin flips, we're going to find a prize. Why? Because we're guaranteed. And we put an expectation here, right? What's the expected running time? And the answer, the answer is 2, right? Half the time you're going to find it in the first go. A quarter, you're going to find it in the second, right? So you can write down the expected. And quite frankly, now the math is really fairly hard to do that. So if you want a hard math problem, you can try to compute this. But in fact, the way I know of an uglier way, if you want a pretty way, it requires taking a differential derivatives of something. So let's not do that.